give the continuation with the previous talk. The topic name for it's been nice, was quite disorder and more.
Thank you. Hello, hello.
You have to switch it off. It's not
From my pocket.
from the device.
Hello, can you hear? Can you hear?
Yeah.
Okay. Thank you. Yesterday I tried to cover too many things and didn't finish. Today I'm going to focus on these pyrochlore antiferromagnets, but there's still a lot of material here. So I'm happy to not finish everything. Please feel free to ask questions during the talk. So maybe that's the best strategy. If we finish some things, and people are able to understand some things, that is better than not understanding anything at all. Okay, so this talk really will focus on one particular type of candidate systems for quantum spin liquids. And in my view, this is really the most versatile system. And I guess this morning we heard a talk from Sayur, which has a lot of overlap with what I'll say over here. So this is the pyrochlore lattice. It's a lattice of corner sharing tetrahedron. So basically you have a tetrahedron, and then the next tetrahedron, one tetrahedron has four neighboring tetrahedra, and they basically share a corner. So in this particular, there's another view which might come in somewhere in the talk. If you look along a particular axis, it consists of Kagome layers separated by what are called triangular layers. And you can see the tetrahedron here, and another tetrahedron here, and then another one here. Okay, so the outline for this talk is as follows. So first, I'd like to talk about ice rules, the ordinary water ice or a particular phase of ice from where the name is derived. Then the concept of spin ice, the idea of magnetic monopoles in this spin ice, and also how it is described by some an emergent magnetostatics. So, and then I'll talk about quantum spin ice in the P model. So this is something which is well understood theoretically. It leads to an emergent U1 quantum spin liquid. And then talk about, so far this is well understood. Then beyond this, beyond the XXZ model, when you start adding additional terms, physics is not fully understood, but I'll discuss what is understood or what we think we understand. But also a variety of phenomena in rare earth pyrochlores that is of interest to understand. And then with summary and open questions. So basically, the ice rules, which are known as the Bernal or Bernal-Fowler ice rules, are very simple. So if you think about water as a crystal, water is basically a molecular crystal. So, and we know protons are tiny objects compared to an atom. I mean, just almost point-like. So if you can forget the protons, the oxygen form a four-fold coordinated lattice. So this is a particular crystal structure, which is a layered hexagonal structure over here. So this, these white circles here are the oxygens. They form a four-fold coordinated lattice, and then there are twice as many hydrogen protons, and these protons are basically sitting in the bonds between these. So there are twice as many bonds here in the lattice, and basically the ice rule is that it has to be a molecular crystal of H2O. So around each oxygen, there must be two protons which are strongly bonded. They are chemically bonded essentially to this. And the other two are far away. They are basically weakly hydrogen bonded. So basically, what Linus Pauling observed is that this kind of a system has a finite entropy because just associated with the positions of the proton, because each proton can possibly be either near this oxygen or near this oxygen. Okay, so there are large number of possibilities, but of those, only those that are allowed are those where you have exactly two near each oxygen and two further away. So these ice rules lead to a residual entropy, and we'll discuss this. And actually, that was already mentioned. It was first derived by Linus Pauling, and basically Bill Anderson in the 1960s. So this was maybe in the 1950s. Bill Anderson in the 1960s noticed that if we consider a pyrochlore system, which is a system of corner sharing tetrahedron, and if you imagine an antiferromagnet on this tetrahedra, basically where the ground state is one where in each tetrahedron two spins want to point up and two down, then you can exactly map the configurations of the ground state configuration of that kind of a spin system to the ice. So he called it a spin ice. But of course, pyrochlore has a certain symmetry, and to have an antiferromagnet pointing along any one particular direction is very, very unphysical. Much later, it was realized that you can actually have real materials, which is what I'll focus on here, for which you have strong anisotropy. These are basically rare earths where you have strong spin-orbit coupling, very strong anisotropy, and if you have a spin at these vertices, basically, which is constrained to point between along the line joining the centers of the neighboring tetrahedron. So it either points into this tetrahedron or into this tetrahedron. And furthermore, if you have ferromagnetic interactions, then remember that these angles between these two is larger than 90 degrees. So a ferromagnetic interaction basically means that if one points out, the other one wants to point in. Then the ground state in one tetrahedron is exactly one where two point in and two point out. And then when you consider it over the whole lattice, this problem exactly maps onto the ice moon problem. And that's what a spin ice is. So that system is then called a spin ice. And we already saw this plot over here in the morning. So first of all, Pauling's calculation is very simple. If we think about if we have n spins, the number of configuration is 2 to the n, but they must be reduced by the fact that each tetrahedron applies a constraint. So you can have 16 possible states of a tetrahedron, okay, each could point in or out. Of those 16, only 6 are ground state. So you have 2 to the n times 6 over 16 to the power n over 2, because the number of tetrahedron, if you do the counting, is exactly n over 2, and there are n states. So the remaining ground state configuration in this count, this is not exact, but is actually quite accurate, is this. And when you take the log of this to find the entropy, you get an expression that looks like this. So the entropy per site is 1/2 log 3. And actually, Jan Oitma and I did a very happy, you can systematically improve this. You can think of this as a first order calculation in something that we did to almost 15, 16 terms. The corrections to this is less than 1%. That's the amazing part of this particular approximation here. So Art Ramirez and collaborators, they were the first to measure the heat capacity of a particular material, dysprosium titanium oxide, where this titanium is non-magnetic, as D0 configuration here. Dysprosium is the magnetic ion, and it's a high spin, but nevertheless, the strong anisotropy makes it Kramer's doublet. Basically, there are two states, two crystal field split states, which are at the lowest energy. So it's like a spin-half, effective spin-half system. And when you measure the entropy, so this is the heat capacity, and the black dots are in zero field. So if you measure the heat capacity and then you integrate the heat capacity or C over T to get the entropy, you find that the entropy change between low temperature and high temperature, it differs from R log 2 by precisely this Pauling value. So that means that if you think that this is R log 2, then there is a frozen in entropy of the Pauling magnitude at low temperature. And that was basically the first experimental observation of this Pauling residual entropy. And of course, if you apply a magnetic field, then it should go up and ultimately go to R log. Okay, so this system basically means that at low temperatures, if we go below this peak, we have a system where only the ice configurations, only those configurations that satisfy the ice rules are allowed. Okay? But all those configurations are allowed. So it's not an ordered system. It's not a particular configuration which is being preferred over here. There are exponentially large number of configurations, but they all satisfy this constraint. So that's an example of what one would call a classical spin liquid. It's a highly constrained, as if local rules, like in a liquid. I mean, liquid has a very strong short range order. There's a strong correlation between where the neighbors are going to be. So we have a highly constrained local system, but there is no long range constraint. Okay? So far away, the system can fluctuate because we have exponentially large number of configurations. Okay, and in such a system, the excitations turn out to be like monopoles. Okay, so first of all, if you flip a spin, so imagine that this is an ice configuration where both these tetrahedra have two in and two out. And now if you flip this spin over here, then both these tetrahedra are no longer obeying the ice rule. Okay, so both this has now three out and only one in, and this one now has three in and only one out. Okay, so they're not obeying the ice rule. Obviously, that is an energetically costly configuration, and it's like a magnetic dipole. Okay, so it's as if it's like, which is what spin one excitation is supposed to be. If you flip a spin, that's like creating a dipole. However, what is interesting in this case is that you can just keep on flipping the spins and by in an appropriate way. And by doing that, what you'll find is that each of the intermediate tetrahedra is back to obeying the ice rules, and you have separated the north pole from the south pole, basically. Okay, so essentially, it's like you have a monopole anti-monopole pair in the system. Okay? And that's basically where the you could call it a plus and minus charge, but in this case, physically, it's really not an electric charge. It really is like a magnetic charge. So it's appropriate to think of this really like a magnetic negative pole and a magnetic positive pole. Okay, so as if these are magnetic monopoles. However, this description that there is no extra energy cost is really true when the only interaction is the nearest neighbor exchange interaction. Okay? In reality, in the rare earth materials, the exchange interactions are very small. They are of order 1 Kelvin. And they are not much smaller, they are not much bigger than dipolar interactions. And we know that dipolar interactions are actually long range. Okay, so in general, they would lift this degeneration. So will all this description, if we want to say that this applies to the materials, then we have to ask whether in the presence of dipolar interactions, is this description still valid? That's not obvious, but there's a beautiful paper actually by Roderick Mosner, Shivaji Soni, and Claudio Castelnuovo, where they came up with this so-called dumbbell model, which is a really interesting model. So what they say, which actually applies extremely accurately even to an exchange plus dipolar interaction model. So the model is the following. So imagine that you have spins over here, okay, which is really an arrow pointing from this side to this side. It's really a dipole. But imagine breaking up these guys into two monopoles, okay, as if there is a plus charge sitting here and a negative charge sitting here. Okay, so imagine replacing every one of these guys by something at the center of one tetrahedron and something at the center of another tetrahedron. Okay? So this dumbbell model is basically a model of various charges sitting at the centers of each tetrahedron. Okay, and then these guys are really monopoles. You can think of it as electrical or magnetic charge. If you want the language of electrical charges is simpler because we are more familiar with it. They have an interaction of this type, which is basically how charges interact. The potential energy goes as 1 over r. However, you have to, in order to define this model in this way, I mean, if you try to do it when r is equal to 0, you'll get infinity. So we need a short range cutoff. We need a short range short range potential has to be defined in self interaction has to be defined in such a way that it matches with our original model. Okay, so you can simply say that as far as the self interaction of each of these guys is concerned, it only depends on the net charge over here. It goes as Q alpha square, where Q alpha is the sum of the charges of all the individuals that you have put over there, times some constant. And this constant has to be matched to give really good agreement with your dipolar plus dipolar plus exchange model. Okay, so actually, this effective model describes the original system very well. But now you see what happens. So imagine that this parameter V0 is large, which is actually true. If this V0 is very large compared to this this energy scale over here, then the ground state is first of all determined by all the Q alpha equal to 0, which is exactly the same set of ground states that we had discussed before. So you want the center of each one of these guys to have 0 net charge, which is exactly what the ice rules are. That is, you want 2 positive and 2 negative, 2 blue and 2 red monopoles in each one of them. Okay, so that is described by this. But then we also know in this case that if you create an excitation where you have an extra one here, the excess energy here and there, they actually no longer, the energy is no longer constant with distance. It actually decreases as 1 over r, which is what monopole charges should do. Think of it as electrical charges if you find monopole confusing. But basically, as you separate them by a distance r, the energy decays. The energy is, they want to stay as close as possible because they have opposite charge. Okay, they do attract, but it takes only a finite amount of energy to separate them. Okay, so the energy of creating such a pair and separating them is finite. Is at the end of the day, when r goes to infinity, this term will drop out, and all that has happened is that you have you have paid a certain amount of cost to create this monopole anti-monopole pair. So this model actually describes really well lots of properties. Okay, and this is one thing that has been you mentioned the Debye-Huckel theory. Debye-Huckel theory is a very well-known theory for basically solutions with electrolytes with positive and negative charges and how they screen and do all those things. Same thing applies over here, except these are really in some sense magnetic monopole anti-monopoles, and you can describe lots of physical properties of the system using this kind of a model, okay, which has been a big success really. Okay. And
you get the excitations.
Yeah, so right, so there are all kinds of probes basically. Of course, you have thermodynamic measurements. You have measurements if you apply electric or magnetic fields to the system. You look at the how those things basically behave. So there's no, I mean, directly measuring actually the most dramatic probe of the system, which I will discuss a little bit. And in the morning talk, Sayur actually gave a picture of that. Is you do neutron scattering, and at low temperature. So first of all, a probe of just the ground state itself. The ground state is characterized by this property that you have 2 in, 2 out everywhere. That amounts to, if you think of this vector actually as a kind of a magnetic field vector, then it's like that field is constrained to have 0 divergence. So this 2 in and 2 out can be thought of as locally a 0 divergence condition. And that 0 divergence condition, basically when you Fourier transform it, it comes in as a condition that that Q dot be dotted with the appropriate vector V field must be equal to 0. And that condition shows up as what are called pinch points. You have special points which are related to actually the Bragg points, where you find strong intensity in some direction, 0 intensity coming out in other directions. So those are observed, in lots of different systems. So it's a direct evidence that the low energy state is one where you basically have this constraint. It's a direct probe of the constraint. Okay. Your question was slightly different. How do we probe that there are monopoles? Well, I mean, the Debye-Huckel theory, which can be used to study the thermodynamics, is an indirect probe. That the excitations are like positive and negative charges, electrolytes balancing each other, or positive and negative monopoles balancing each other. I mean, I don't know that there's a direct probe of the fact that there's a 1/r interaction between them. I mean, that may not be so easy.
Or that they exist. They are
So
separate. I mean, what?
right. So basically, at low temperatures, they go away, and these are. I mean, their number is not conserved, right? In the ground state, they are absent. So if you go into low enough temperatures, then they are simply gone. As you raise the temperature, you start creating lots of these guys. You create a density of these guys, and that's where the Debye-Huckel theory comes in. Because then the thermodynamic behavior is governed by a density of these positive and negative charge monopoles. Okay? And that seems to describe the system well. Okay? But that's not looking at individual guys, but it's looking at an ensemble. It's not, to my knowledge, I don't know that there's a direct probe of a single monopole or just a pair of monopoles and how they interact. Probably not easy. But yeah, I may not know. Yeah.
Is it a model or they really exist?
No, it really exists. Sorry.
That is one thing.
No. I'm saying it really exists. Yes,
really
yes.
exists.
A very good question. Yeah.
Yeah.
I'm saying that this really does exist. This behavior, so there really is a model. There really is an experimental system. There's this one. There are more. This is one of them. So there are a class of rare earth pyrochlores. Actually, I will talk about maybe the whole class of systems where the dysprosium or whatever the rare earth is, that atom forms a pyrochlore lattice, and it has strong anisotropy, and the strong anisotropy causes the low energy state of each dysprosium ion to have a spin which either points this way or that way. That's all very well established. And furthermore, what is well established is that at low temperatures, you have this constraint, that 2 in, 2 out constraint can be directly seen in neutron scattering by just these pinch points. Furthermore, at higher temperatures, you can describe the thermodynamics of the system, just like Debye and Huckel described an electrolyte, of positive and negative charge. So it's as if the thermodynamic description of the system is that of basically oppositely charged monopoles. There's no charges here. There's all neutral system over here. So the only charges we are talking about are magnetic charges. Right. So this is real. I mean, this is all observed. Right. Very important question. Yes. Okay. All right. But after this, it's all theory. Sorry. I mean, there are experiments, but we'll see that the agreement is not as good. Quantum is just much harder. This was so far classical.
A single pair.
No. No, you can have if you raise the temperature, you'll have a dilute gas of these guys. And then they will be screening each other and they will be moving around. So that's where the Debye-Huckel theory comes in. At low temperatures, these guys are absent, but then they will be very dilute. But there still will always be a density of them. And by the time they become dense, then this description breaks down. There's no point in thinking in this language. Okay, all right. Quantum. The subject is quantum spin liquid. So let's imagine. So this was our model so far. Our model was basically just a pure Ising model. There was no quantum fluctuation. But let's add to this a transverse coupling, a coupling which is of this form, or there are lots of, you can have some other forms as well. And suppose this coupling is weak. So lambda is small compared to 1. Then what happens? Well, basically, this is the first. This is one Hamiltonian for which we know the answer very well. First of all, whenever you add such a perturbation to a system which has many degenerate ground states, so this thing we said, has exponentially large number of ground states, which is why there is a residual entropy of this system over here. When we add a perturbation like this, we need to do degenerate perturbation theory in this many body substrate. Okay, but in general, whenever you have such a situation, quantum fluctuations can do one of two things. They can lead to a selection of order. They can actually pick out one state out of the many degenerate states, or one small set of states. That is called order by disorder. That's very common phenomena, and I might have an example of that later on in this talk. But the other more interesting example, something that we are much more interested in because that leads to a new kind of a macroscopic quantum phase of matter, is that it doesn't select one particular one of the I states, but it really leads to a highly resonating phase, which is a linear superposition of all of these states. Okay? That is what a quantum spin liquid would be. So in this case, the claim is that when you add this perturbation, it will actually lead to quantum spin liquids. And the reason is very simple. So let's do the perturbation theory. So if we treat this as H naught, and if we treat this as our perturbation over here, well, you can see that, first of all, we have to do degenerate perturbation theory. First of all, in first order of perturbation, the matrix element is 0, because what this does is it flips a pair of spins. If you flip, say, a pair of spins like this, so let's say it flipped this spin and this spin over here, well, then this pair of anti-parallel spins, one going in and one going out, if you flip it over here, that's okay, because that basically this tetrahedron stays in the ground state, but both this guy and this guy are no longer in the ground state. So you go out of the subspace. So if you think about degenerate perturbation theory, we are not interested in going out of this subspace. In first order, you are simply interested in, are there any matrix element connecting two spin I states? Well, no, they're all 0. Well, then let's go to second order. Well, second order perturbation theory, you want to start from one of the I states, go to some intermediate state, and then go back to the I state with some energy denominator. Well, it turns out you can flip any anti-parallel pair of spins, and every spin ice configuration has exactly the same number of spins that you can flip, exactly the same matrix element, exactly the same energy denominator. And so the second order, what you get is a constant. The effective Hamiltonian is second order is a constant, leads to nothing, no selection whatsoever. Okay, everything remains as it is. So you have to go to third order. Unfortunately, third order is enough in this problem. When you go to third order perturbation theory, so we want to now go from some state to a second state, then to one state out of the manifold, then to a second state out of the manifold, and then back to another spin I state, the two energy denominators. And now it turns out that there is a very interesting possibility, which is called a ring exchange. There's a tunneling that can happen every time we have a spin ice configuration. So imagine that I'm showing the Kagome plane over here, and I'm not showing all the out of plane triangular spins over here, which form the vertices of these tetrahedra. Let's just focus on this. And let's just focus on the 6 spins which are around this corner over here. If we have a configuration in which in every tetrahedron, one of these points in and the other points out, okay, in this way over here, then in third order perturbation theory, you can flip all 6 of them and basically go to a configuration like this, and you can check that in every tetrahedron, you still have one in and one out, and the other 2 are obviously in and out, which are not shown over here. And so you are going from one spin ice state to another spin ice state. So basically, what this leads to an effective Hamiltonian that is a ring exchange. So all that happens, no other Hamiltonian. Now the effective Hamiltonian that one has to study, assuming that lambda is sufficiently small, is basically this ring exchange Hamiltonian. Okay? And of course, that's still a non-trivial problem, but this at least should make you hopeful that maybe the ground state of such a system is going to be some kind of a resonating state rather than selecting a particular state, because it's causing resonance between different configurations. there are various tricks one can apply, which are not so important, whereby the model can be made exactly soluble, where the ground state becomes an equal superposition of all spin I states. But to really get down to this big exchange model, one has to do something numerical. Okay, so you can do some Monte Carlo simulation or variational calculations, and I think the most, in my view, the most impressive work is by Nick Shannon. He has done a number of work, basically, essentially at the end of the day, showing that you end up with a resonating valence bond state as the ground state. So the state that arises in this case, once you know that it's a resonating valence bond state, then you can build a field theory description for this, which was actually done earlier by Leon Bellens, Matthew Fisher, and collaborators. Basically, what you end up with is something that is an emergent quantum electrodynamics, okay, without charges. Okay, so basically in vacuum. So what you have, you can think of this. Let's say now in this new language, it's convenient to think of SZ as an electric field, and S plus basically being described by a vector potential, where this A and E basically obey this kind of a canonical commutation relation that we expect for vector potential and electric fields. Okay, in quantum electrodynamics, we have this. This is simply related to the commutation relation between Sx, Sy, and Sc. So the spin commutation relation, when you write it in this way, can be translated into this. The fact that the divergence of E is 0, that condition basically is is basically what the ICE rules are. They tell you that this Sc vector, it obeys this kind of a divergence less condition. The divergence of E, this is a discrete divergence on a lattice, is 0. And the spin ice term, the ring exchange term, basically, if you write it as e to the I something something something, then this sum over placket of this A plus minus etc., that is really nothing but a representation of a discrete curve. So that basically is telling you that you have two conditions. In some sense, you want to minimize this, and so the effective Hamiltonian is of the form divergence of E square. It costs energy to put something here. Ground state will have none of it. And you have a term coming from here, which will be just cosine of curl of it. And you can add another term over here. Basically, in some sense, it is put in by hand over here, that you want to have this electric field to have, in our model, just the values plus or minus half. I mean, we don't want, we want this SZ to be plus minus half, but you can imagine making it into a soft constraint, EAB square or EAB square minus a quarter or something like that. I mean, basically, you want it to take only two values rather than all values. So a soft constraint will be to just put a U over here. So this Hamiltonian now, when the divergence of E is 0, you can basically see that this will end up giving you, in that limit, just an electromagnetic Hamiltonian. You will have an E square term, and this basically curl of A, we call that B, and expand it out, this will give you a B square term. So this theory actually predicts that you should have emergent force. So this has nothing to do with electromagnetism of the outside world. These are all electric and magnetic fields associated with the spin configurations. Okay, so it's an emergent electromagnetism, and one predicts, at least in numerical calculation, that there should be photons, and basically even in the absence of charges, just like fluctuating electric and magnetic field can lead to traveling photons that can travel through vacuum. Even in the absence of any charges over here, when this divergence is 0, you should have this kind of a photon, and there's a certain. But these photons are made up of spins, so they can directly couple. Actually, it turns out, to neutrons, and so people have made very interesting predictions for what the neutron scattering spectra should look like. Now, unfortunately, this has not been observed experimentally. So if it was real, this would be a major triumph. But it has not been seen experimentally. Okay, it's very different from Goldstone modes, and people argue that it's actually more stable than Goldstone modes, because if you're familiar with Goldstone modes, those are gapless excitations, but they depend on symmetry. And in solid state systems, in reality, you don't have symmetry. You always have something that breaks the rotational symmetry. You always have some spin orbit coupling. You always have some dipolar coupling. So in reality, you don't have any Goldstone modes, okay, in real solids for spins, because you always have some symmetry breaking. But this one is argued to be much more generic because it's not based on symmetry. It's based on this emergent theory over here. So people argue that these should be observed. But first, you have to find the space. Any questions?
So what is the signature? I got some.
Right. So the signature. This is potentially something that is directly observed. So this is what this is showing over here. Sorry, I didn't explain what this is. It's some directions in the Brillouin zone. I'm sorry if you have to come very, very close over here to see. There's some HH0 and something. So yeah, there's a linear dispersion around the Bragg points, around the special points of the Brillouin zone, which correspond to gamma points. And there's linear dispersion, but the spectral weight goes to 0 at those points. It's very different at Goldstone mode. At Goldstone mode, the spectral weight diverges at these points. And this is coming from an explicit calculation that Shannon and collaborators did, where they predict exactly what the neutrons should see as a function. This is S of Q and omega, if you like. So if they do a Q and omega resolved neutron scattering, they should just see this. You have this space. Okay. All right. So now where should we look for this? So there's a whole class of rare earth pyroclores which have this stoichiometry over here, A2, B2O7, where both A and B sides form corner sharing tetrahedron, but one or both could be magnetic. The ones that have been studied the most, the B side, let's say, is non-magnetic and is transition metal, and A side, which is the rare earth, is magnetic. And you can have many different things over here. Okay, so F electron systems have large spin but strong spin orbit coupling, so they give you nice. They can give you nice Ising systems. They can give you a nice crystal field doublet state, which actually can be Kramers or non-Kramers. Kramers means that the two states are related by time reversal symmetry. Non-Kramers means that they are not. They are related by some other crystalline symmetry. Okay, so lots of possibilities over here, but where should we look for this emergent QED? Well, first of all, the anisotropy should not be too strong. Okay, but because if my XY coupling is too weak, then the problem is that the tunneling times will be so low, that the times will be so large, because it will take so long for the system to tunnel from one configuration to another that it will easily take the age of the universe. So if the perturbation is too weak, then the system will be stuck in a particular state. Okay, this is what happens in water ice, for example. Water basically goes into a particular configuration and it's frozen there. Okay, if you go to low enough temperature. Okay? There's thermal rearrangement, but if you go to low temperature, then basically it will be stuck. There will not be any quantum tunneling, although there were a lot of theories early days about quantum tunneling in water, in DNA, this and that. But as far as I know, it doesn't happen, okay? Because in some sense, the matrix elements for tunneling are too small. So if your perturbation is very weak, you're not going to get anything. You're going to basically be stuck in the classical ice configuration. But you also don't want it to be too large in some sense. Okay, so basically you need uniaxial anisotropy and quantum terms that are not too small, but perhaps they can't be too large either, because then this whole perturbation idea will be wrong and something else might happen. Okay, all right. So the material that is best understood is this one over here, ytterbium titanium oxide. So this is a Kramer system. Okay, this is a doublet ion related by time reversal symmetry, and this experiment actually goes back to the 1970s. What you see is that the specific heat, this is a plot of the specific heat. There's a broad hump over here, but then there's a very sharp peak at low temperature, at around 200 millikelvin. Sorry, the scale is not so obvious. This is in Kelvin over here, going up to 5 Kelvin over here. So there's a peak around 2 Kelvin, and then there's a very sharp peak around 0.2 over Kelvin over here, 200 millikelvin. Okay. So this material basically is a pyrochlore material, and one of the challenges really is how to determine the exchange parameter. We don't know in many of these highly frustrated systems, how do we know what exchange parameters are there? So that itself is a challenge. The one thing that people have found very useful is you apply a strong magnetic field. In weak fields, you don't even have nice excitation. So you can't easily do any spin wave calculation or something like that and deduce the exchange parameters from there. But what you can do is you can apply a strong enough field so the system is fully polarized. And now the calculations are easy because no matter what exchange parameters you have, if the field is much larger than all the exchange parameters, the ground state is going to be polarized. And flipping a spin, you can easily do the calculation. It's like a tight binding mode. The spin excitation spectrum can simply be gotten by a very simple spin wave type calculation. And that's basically what Kate Ross and Leon Bellens and collaborators did. And you can see that, just by fitting the experimental data with the theory looks very clean because experiments are always noisy. They were able to reduce the exchange parameters, and they basically, by symmetry of the lattice, it turns out that the nearest neighbor Hamiltonian, assuming it's sufficient, already has 4 parameters over here. There is this guy over here. This is our spin ice model. Then there's something that we just wrote down before, this J plus minus model, which leads to, within perturbation theory, this nice quantum spin ice phase. But it has 2 other terms over there. It has this thing called J plus 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 minus plus minus. So in other words, it's not like the plus minus term, it's a plus plus term. But it also has this JZ plus minus term. So it goes with a Z with a plus or Z with a minus. And these zeta, these gammas and these zetas are actually just phase factors. They are third roots of unity. So they are not parameters over here. They are just known numbers. They are dictated by the symmetry of the lattice. Okay, so even in zero magnetic field, you already have not just 2 parameters, which we would have liked, but 2 extra parameters. So, and they determine these parameters, and then you have to ask, okay, so how good is their parameter determination? So what? Okay. Unfortunately, what happens in these parameters is that it turns out that after this one, we want this one to be largest. Among these 3, the largest turns out to be this one over here. The JC plus minus actually turns out to be larger than these parameters. And that's not a good thing because it leads to order by disorder. Remember, I was telling you about something else can happen. If you have JZ plus minus, then already in second order perturbation theory, it actually favors, it selects out some of the states, because what happens is in second order perturbation theory, well before the third order, it actually creates a coupling between the third neighbor. So this guy starts coupling to this guy, and that coupling turns out to be ferromagnetic. In other words, it wants this spin to be parallel to this spin over here. And so what that does in the set of all ice rules obeying configuration, it picks out a Q equal to 0 configuration. In other words, the pyrochlore lattice is a 4 sublattice structure. So each tetrahedron has 4 spins. They are like the 4 sublattices. And so every spin that belongs to the same sublattice must point in the same direction. This system turns out to be ferromagnetic because when you add the 4 spins of a tetrahedron, you don't get 0. There's a net moment pointing in a particular direction. In fact, along the 1, 0, 0 or equivalent 6 directions over here, depending on which of the 6 configuration you pick on a particular pyrochlore. So this should actually lead to ferromagnetic order, and we believe that's basically what happens over here. Anyway, so you can study this effective model with J3 by classical Monte Carlo, and when you do that, you'll get, depending on how small this J3 is, you'll get this peak associated with the spin ice, and then at really when J3, when temperature becomes comparable to J3 over here, then you will see a sharp peak which corresponds to the setting in of the Q selection of the Q equal to 0 state. This is what the order by disorder phenomenon is. And as you make J3 bigger, of course, this will start to overlap with this over here. But then this perturbative description is no longer good. What we did by numerically, again, you can also do a calculation using this method called numerical link cluster expansion, which can be done even when all the parameters are of order 1. But unfortunately, that can only be done at relatively high temperatures. And you can see that with the parameters that they had come up with, without any further parameters, basically one can describe the higher, this is a log scale over here, the higher temperature now. But of course, the NLCE calculation breaks down below some temperature, so we cannot go up to here. Nevertheless, what one could do is one could calculate the entropy reduction from our numerical calculations, which is, let's say, given by these blue and green lines over here, coming down to some temperature. And one can calculate the entropy from the experimental measurements. And you can see we don't really have a nice classical spin ice in this case. A classical spin ice would mean that it comes down, and then at this fouling value, it saturates over here. It stays there, okay, forever. So we don't really have any clear plateau over here, but you can see that there's some kind of a structure over here, which is suggestive that this model is probably not very far from turning into a spin ice. Of course, ultimately it orders. It just ends up becoming ordered. So basically, as I mentioned, that in principle, you would think that it's a ferromagnetic order, so it should be relatively easy to see. But unfortunately, it is not, because there is canting. All these parameters, they cause a certain canting, and the ferromagnetic order sits at the same point as the Bragg peaks. So it's not easy. It's still controversial whether this is the full physics of the model or not. Okay, but certainly many of us believe that that the correct physics of this model is that ultimately the system goes into an ordered ferromagnetic state, canted ferromagnetic state. Okay, so that if we want to go beyond this system over here, the moment all these couplings become of order 1, which is the case in the system, there is really no hope other than to do really full-scale computational study. There's no perturbation theory or no field theory that will be able to solve this kind of a problem. You basically have to do large-scale numerical calculation. So, not sure I want to go into great detail over here. How much time do I have? Sorry. Okay. All right. So let me just say a few things over here. So if we go away from that limit, which is Ising dominating, and then other terms are perturbation, then you might as well start again from the classical model, okay, and then develop intuition from the classical model as to what is going on, and then look for parameter regions where interesting quantum spin liquid type behavior might arise. Okay? And then maybe do some studies. And unfortunately, our ability to study quantum models is fairly limited. So basically, one place to start, for example, is the Heisenberg model. The Heisenberg model which is SI.SG. This model can also be written, because it's a sum over all nearest neighbors. This can be written as a total angular momentum on a tetrahedra square. Okay, this model can basically, apart from some additive constant, basically can be written in this way. And so that tells you that the ground state will be achieved provided the total angular momentum is 0 on each cluster. But now, classically, we have 4 spins over here, and they have to add up to 0, okay? And it's a vector. So for 4 equal length vectors to add up to 0, there are just enormously many ways to do it, because you can imagine, let's say 1 and 2. Okay, so you can see that. Okay, let's consider 1 and 4 over here. These 2 vectors basically could be separated by some vector distance a. And 2 or 3 have to be separated exactly by the same vector distance for them to add up to 0. And you can see that these guys can be rotated around this axis over here by a certain angle. So there's a lot of freedom, a lot of possible ground states over here, much larger, in fact, than even the spin ice configuration. The Heisenberg model is, in some sense, even more frustrated. Okay, there's an enormous, and what is believed is that it's so large that this model remains disordered. Even on the Kagome lattice, it is believed that thermal fluctuations lead to some kind of a selection ultimately, but there is no order by disorder in this case. Okay, and in this case, actually, the answer to the quantum problem is still not clear. What happens to the quantum Heisenberg model on the pyrochlore lattice? Okay, let me just make this the last stop over here. Otherwise, so basically, there's another very useful analysis that one can do before doing any numerical calculation, and that is a symmetry analysis. You can use group theory, you can use irreducible representation, basically to write a Hamiltonian with all the 4 terms, basically in terms of the squares of different types of order parameter. Okay, and this can also be diagonalized. You can ultimately write it in this form over here. So these are squares of certain orders, like all in, all out order, ferromagnetic order, something called the Palmer-Chocker, something called psi2 and psi3 or gamma 5 order. Not going into the detail of this, these are different representations, irreducible representations of the tetrahedral group. You can write it as a square of this, and the sum of the squares have to add up to 1. This is a spin length constraint. So what is interesting in this analysis is that anytime you find that one of the parameters is smaller than all the others, that immediately tells you that the ground state must be that parameter equal to 1 and all the others equal to 3. Okay. So you will be in a particular phase. You'll be in an A2 phase or T2 phase or an E phase or T1 A prime. So most interesting things happen when more than one of them are equal. So it's at the phase boundary of these phases that all kinds of additional degeneracies happen, and then you can start to have order by disorder, or you can have possibly a spin liquid. Okay, so let me just stop here. Okay, so we had a recent paper, we are writing another paper, so there's still a lot of work going on what are possible. I'll go into the details over here, and I didn't bring up other materials, but let me just say that people have synthesized maybe of the order of 20 or more materials which are of this type, where you have spin half system. But to this day, we don't have any system where we can say, oh, look, we have found a quantum spin liquid in this case. So if they found something like a photon, that would be an example of a quantum spin liquid. So to my knowledge, that has not yet been found. There are some candidate materials, but still nothing. So basically, this is a summary of things that I discussed over here. I guess one question that I think is important conceptually: why has it been so difficult? I didn't discuss many of the other examples yesterday. I talked about the Kagome, the triangular, the honeycomb cation. People have a lot of candidate materials, and yet no quantum spin liquid has yet been found in a convincing manner. What is the reason? Why is it this quantum spin liquid state is kind of like the quantum Hall effect, fractional quantum Hall? But fractional quantum Hall effect exists. We know there are experiments that tell you there's fractional quantum Hall effect going on. So why is it that we don't have quantum space? Is there something wrong with the theory, or is there something particularly subtle over here? I think there is one answer that people suggest, and the reason why the quantum Hall effect has been so successful is because there's been a 50-year preparation for the material. The semiconductor technology required people to develop really, really high quality samples. I mean, people spend, billions of dollars just to improve the sample preparation for the semiconductor MOSFETs so that they are really clean, they're really high quality, and that is why they can show all these beautiful phenomena. For many years, there were only one or two groups that could show those samples. Now maybe there are a few more, but nevertheless, that technology has been there. Whereas here, we have a lot of candidate material, but nobody has tried to put in that much effort to improve the sample quality. And you always have disorders, you always have, extra things here and there, stuffing, people call it, or other things. So, and this is one answer. Until the samples are of really high quality, you're not going to see this kind of case. And if you're studying a whole lot of systems, you can only get indication, okay, maybe there's something here, and then you move on to something else, and then you move on to something else. So perhaps that is an answer. And, I don't see any fundamental reason why quantum spin liquid should not be employed. The technological motivation is really not as strong as for semiconductor. The semiconductor technology is just too important. Some people argue that this could be the basis for the next generation of quantum technology, like quantum computers and so on. But for that, people are looking at many different, not the only. So I don't know if in the near future we are actually going to have a quantum physics. Unfortunately, I'll have to end on that pessimistic note.
Okay. Thanks. Uh, Thanks. Question from
Quantum entanglement can enhance your, whatever evidence you're getting. Theoretically, whatever signature you are getting, quantum entanglement can enhance.
Yeah, so this is the moment we talk about a quantum spin liquid with a highly resonating state that will have very large microscopic quantum entanglement. Non-local. Local means you have only boundary associated, only the degrees of freedom here, the boundary are entangled. But in a quantum spin liquid, you really have, I was discussing the other day, you really have non-local quantum entanglement. So that has to be present. But it's true in the fractional quantum Hall effect. You will not get fractional quantum Hall effect without non-local quantum entanglement. So in that kind of entanglement exists. A priori,
How does one float that? Because in
It's
the
very hard.
transport, it's easy.
it's very hard.
It's possible.
So here there is a possibility of a thermal quantum Hall effect. That I discussed last time. Again, it remains very controversial because measuring it is not easy. Electrical measurements are easier than the thermal measurement because you have phonons, you have other degrees of freedom, and they also are competing. So it's not easy. And there are other probes that people have come up with. But first you have to find a material, right? Or maybe first you will find some signature that looks like a really strong signature. But then somebody has to really improve the quality of that.
The thing, the absence of order,
Yeah.
and then a large entropy. Those are some signatures.
Those are
Lot of
very
candidate
good
material.
starting point. Yes, that's
Lot of materials
preparing
is-
the base. Yes,
Yeah.
and that certainly exists.
Yeah, that
The
exists.
classical spin ice, we have very good experimental evidence. So that exists. That you have absence of order, you have large entropy, and in that large entropy, you have monopole-like things. Those all exist, but that's not entanglement. There's no quantum yet. Yeah, we need a little bit more. We need something else, to probe the quantum nature of the.
That would be
Photon is the real. So if they actually see this emergent photon, the tendency there, that would be a proof that yes, you have found something very interesting.
I have a naive query rather than question. As you say, or either sample may be not as ideal as theory suggests, and also how robust is theory so the small perturbation will change anything.
That's a very good question.
This is one
That's
thing.
a really good question.
Ah,
Yes.
And another point is the real system or reality is very different. For example, we are thinking about ideal pyrochloride.
Yes.
But for example, Yen-Teller distortion. This electronic system are coupled with the lattice whether lattice is changing at low temperature. I'm not sure. I've just several things
So, the very good
coming
question,
into
yeah.
mind.
Yeah.
Whether are they remaining perfect pyroflow or they are
Really,
changing?
really good question. So first of all, for the Kramer's systems, there's no yarn feller discussion. Because
No,
the-
I'm not talking Yantala, but you know, the
yeah, in the
lattice
non-Kramer's
is
actually-
changing.
So
Yeah.
in the non-Kramer system, actually, that is very sensitive.
Yes.
The point you raised about that, the non-Kramer systems are actually very sensitive to distortion. So the Kramer's systems don't, because these are time reversal symmetry related to state systems, and they're not very sensitive. As far as we know, there is no lattice distortion. So that part, but you had several parts there. Sorry, I forgot your earlier part. There were a lot of good questions there. Let's see. What was your first point?
I said that how robust is
How
theory,
robust,
so the
right.
small perturbation.
Right. So
Yeah.
that question is always a good question, and we believe that this is robust. It's robust in again, how robust means very hard to put a quantitative number by theory. So theory can only tell you that it is robust to small enough perturbation. So in a theoretical sense, in a renormalization group sense, if you like, in a perturbative sense, that if the perturbation is small enough, this is robust. But what's small enough? 10 to the minus 5, or is it 10 to the minus 1? That's a hard question now, because that's a matter of numbers. And so theory cannot answer it. Only computations, and computations are not really good enough to answer that question. Okay, that's one thing. There were several other questions. I'm sorry. Yeah. Yeah. Good questions.
Any other question?
There was this
Yeah.
like this tantalum sulfide, I think there's
Ah,
tantalum
that's
sulfide
a
or
different.
selenite.
That's a different.
I
Yeah.
mean, that's a more a
That's more like
semiconductor
a layered system. Yeah.
system.
Yeah.
So what's the status of that?
So that one apparently a particular tantalum diselenide maybe forms a Kagome or triangular layer, and perhaps it has a. I don't know. I don't. There are many spaces where people have claimed that there is a spin on something. To my knowledge, it's not. There is a much better chance of seeing these phenomena in cold atoms or in Rydberg atom systems, because they are not, in some sense, they are completely artificial. They are engineered, right? So you can build in the interaction that you want. That's a great advantage. But on the other hand, they are not like a real material. Real materials have many other things going on. And so finding something in real materials is much harder.
Okay, so if there's no question, thank you.